Okay, welcome everyone to this talk on storage I/O control for network-attached storage data stores. Storage I/O control is a feature that we released in vSphere 4.1, and at that time it was only for VMFS-based data stores. In 5.0, I'm glad to announce that we are launching this feature on NFS data stores as well. Last year, we had a huge demand from a lot of people who came and asked for it for NFS data stores. Now, just to make sure that we have the right audience for the talk, how many of you are using some NFS-based data stores in your virtual environments? Wow. And how many of you have never had a storage performance problem? Okay, there's one person in the back. We would like to do further interrogation after the talk. But for the rest of you, you are at the right place. So my name is Ajay Gulati. I am one of the R&D staff members who worked as part of the team to actually develop this feature, both in 4.1 and 5.0. Now, here is the usual disclaimer, which says whatever we tell you in Vegas stays in Vegas, but that's not true for this feature. Everything is released, and you should be going back and using the feature as much as you want. Now, the outline of the talk is basically I'll give a brief overview of the SIOC feature, which some of you may have already seen last year, but for the others, just to talk about what the feature actually does. Then I'll go into some really gory technical details of how it works under the hood to really show that how it is doing what it is actually doing. Then I'll talk about some case studies to highlight the use case of the feature in a real virtual environment using some micro as well as macro workloads. Then discuss a few best practices around using the feature in your environment. And finally, the coolest part is what's next. What are we looking at? And I would like to get some guidance from you to ask what are the major pain points and what next should we be doing after storage I/O control. So what's the problem we are trying to solve? This is a typical virtualization environment where you have a NAS-based data store, which is shared by multiple VMs. And some of the VMs may have higher priority or more importance as compared to other VMs. And on a normal day, things go well and good. But it's quite possible that because of one VM really hitting hard on a data store, everybody else would see the performance problem. And in this particular case, the critical VMs on the left are seeing the performance problems because of one non-critical VM, which is really hitting the data store hard. Now, if you are a storage admin, what's the four-letter word that comes to your mind when you see this? You don't have to say it. Keep it in your mind during the talk. We would like to replace that word with a different word by the end of the talk. So what you would like to see is the scenario on the right-hand side, where when one VM is trying to hit hard on the data store, the other VMs are actually not as impacted. And you should have some way to actually control this behavior, that who should get how much when there is contention on the underlying data store. So how do we give you that control to tell us which VM or which virtual disk has higher importance? For the last almost 6-7 years, we have been shipping these controls for CPU and memory, which is called shares. And we also have a control in terms of limits. And high shares means higher importance, low share means lower importance. So when there is contention, the high share VM would get more resources. So for storage I/O control, we are adding a similar control for the data store that you can now specify at the per VM or per VMDK level. So if you specify at the per VMDK level, then if the VM has multiple VMDKs on the data store, the aggregate of that is that VM's control on the data store. Now, if you look at a real environment, what's the actual goal of the feature once we have this share setting? And why is this a hard problem to solve? Why did it take us so long to actually do this thing? Now, what happens is that the VMs are essentially running on multiple hosts, which are accessing the data store in a distributed manner. And one VM can essentially put a workload which would interfere with all other VMs. Now, if a feature was being built on the shared storage side, they actually have much more visibility where they have every I/O coming through them. But we are building this feature on the VMware side, on ESX side, which means now we have a distributed access problem where different VMs are running on different hosts which are going to the same shared data store. And the goal for the solution is that we want to still do a better performance isolation between VM workloads while utilizing the array at the highest possible utilization, or without underutilizing the array in any possible way. So just to briefly mention that control again, as I said, you can set per VM shares. So in this case, I have just, for an example, given the shares to the VM. It's 10 shares from 10 to 50. And if you think about it, different hosts now have different number of shares or different importance. So in order to really solve the problem, we have to now somehow give more to a host, which would further give more or less to the VMs. And that's why it becomes a much more harder problem to actually solve. Before I go into technical details, just a quick overview of how to use this feature. And the feature is actually very easy to use. It only has 2 steps, out of which one is actually optional. First is you enable the feature on a data store. And how you do it is you go to the regular data store screen, and you see the storage I/O control is disabled on this data store, on the Properties tab on the data store. Now, if you want to enable it, you click on the Properties, and it shows you the box where it says Storage I/O Control, and you can see there is a checkbox there which is currently not selected. You just select the checkbox, and once you do that, the feature is enabled. That's it. You are almost done with using the feature. Now you can also look at which all data stores you have the feature enabled and disabled on a single screen, where there is a separate column now that shows Storage I/O Control, and in that column it shows what are the data stores where it is running or not running. Once you're done with that, here comes the optional step, which you may or may not want to do, which is that you can go to the VM Virtual Disk tab, and you can see what's the current setting in terms of shares and limits. Let me just briefly explain these 2 settings. Shares, either you can pick a canonical value, low, medium, high, or you can set a custom number there. What this essentially means is the low, medium, high, they map to essentially 1,000, 2,000, and 4,000, which is ratio 1:2:4. What that says that if there is contention on the storage, then the performance would get allocated in this particular ratio. What exactly would get allocated in the ratio, I would cover during the more technical deep dive part of the talk. Second control is limit. Note that the limit that you set is in terms of IOPS. So if you already know that you want to set a limit on a VM for 500 IOPS, you can go ahead and set it. But in some cases, you may know that you want to limit in terms of megabytes per second, not in IOPS. In that case, you can easily convert your megabytes per second number as long as you know roughly the approximate I/O size of that workload. Now, there are different ways of getting I/O size also, and we can talk about that at the end of the talk. But if you know roughly the I/O size, you can easily convert your megabytes requirement into a IOPS requirement and set it here. Now, once you are done with that, you can actually go to the screen, and it shows you what's the actual value for all the VMs on a single data store. Note that if you have 2 VMs running on 2 different data stores, then those shares are not even comparable because they're going for different resources. All you need to worry about is, for a single data store, you can get a list of all VMs on that data store, and then you can look at the share value and the limit value, and it would actually tell you how things compare on this data store for all the VMs that are running on the data store. Now, just to give you a very simple example of what exactly happens when you set these numbers. In this case, there are 2 VMs. Both are running a simple micro benchmark, which is IOmeter, and doing 16 kilobyte random read I/O. And the shares that we have set here are 1,000 and 2,000. Now, if you look at without SIOC, what happens, and these VMs are running on 2 different hosts. Now, without SIOC, what happens is both VMs get roughly the same IOPS and the same latency. That's because they're running on different hosts. Each host is sending some amount of workload to the array, and there is literally no control. But if you look at with SIOC, the number of IOPS is roughly in ratio 1:2, and the latency is in the inverse ratio, which is 31 and 16. So what SIOC allows you to do is essentially, if you have a data store that can do 3,000 IOPS, you can divide that 3,000 IOPS differently between different VMs and have control over that. And VMs would see higher IOPS or lower latency based on the setting that you have done. Unfortunately, we don't have the technology to convert that 3,000 IOPS into 10,000 IOPS. For that, you have to go to the storage vendor. But once they have given you some IOPS, rest you can do using SIOC. So what this does is the VMs would get IOPS in ratio 1:2. Now let's look at how it actually does it. What's the under the hood detail of the technology? And essentially, there are two components to the approach. One is detecting the congestion. For any resource management technology out there, you only want it to kick in when there is a resource problem. If there is no resource problem, you don't need any resource management technology. So in this case, in order for us to kick in, we have to detect when to kick in. And the control for that is basically the overall average latency on the data store. We monitor the latency on the data store. If it's too low, it doesn't matter who has high shares and who has low shares. Everybody would be able to send the workload that they are sending because the problem is not there yet. Once the latency hits a certain congestion threshold, and that's the only setting in the feature that is something that we do automatic, but I'll talk about how to set it manually if you would like to. Once the latency hits this congestion threshold, that's when SIOC says, oh, the data store is running at this latency. Now I need to make sure that the VMs which are more important see a lower latency, and the VMs that are less important see maybe even a higher latency. Because the job is to reshuffle latency and IOPS between VMs. And once it is detected that, the way it would do it is a two-level approach, essentially. It controls the number of IOs that are issued from each host. So in the previous example that I gave, there were two hosts, and I had VMs running on hosts with different shares. I would like to control how much each host can do, and then furthermore, in the host, we would control how much each VM can do. And by doing that, we can actually give a per VM isolation. But the whole feature is very dynamic. It's not a static setting. It's not that if you set ratio 1:2 or 4, that we would give them some numbers in ratio 1:2:4. If a high priority VM goes idle, then as soon as it goes idle, other VMs would be able to use that capacity on the data store. It's completely work conserving in that sense, and it would take care of these idleness bursts. And I would show in the case study that when we make some workload idle, that how it makes sure that you still get the highest utilization from the array. Now, as I mentioned about, there is only one setting, which is this congestion threshold. Now, how do you set this setting, or what exactly does it mean? On the right-hand side, I'm showing a plot of total data store load, which is roughly the number of IOs that you keep in flight on the data store. And on the y-axis, I'm showing the throughput. Now, this is a typical canonical curve. You can run it on most storage data stores. You would see a behavior like this, where initially your performance would increase because you are trying to be more and more concurrent, and you are trying to utilize the devices, or if you have multiple disks backing up the LUN, you are trying to utilize all of them. But once you reach a certain value, after that, your throughput would almost flatten out. What you would end up seeing is just pure high latency, and the latency would keep on increasing as you increase the load. Now the question is, where should you set your latency threshold to be? Now, ideally, you want it to be lower so that you can start getting isolation sooner than later. But if you set it way too low, then you may not be even operating your data store at the highest utilization, because SIOC would try to throttle the workload once it hits the congestion threshold latency. So we have set a reasonable default based on our experiments and what the data that we gathered on multiple storage arrays, and the current setting is 30 milliseconds. But this is something that you can change in your environment. For example, if you are running a VM which is more latency critical, and you don't care about operating your data store at the peak throughput value, so you can set the latency to be lower in that case. And if you set it to 20, that would mean that as soon as the device latency hits 20, SIOC would start kicking in. And you would be operating your device at 20 milliseconds, and it would be somewhere on that throughput curve. You might be operating your device at 90% of peak throughput. But that's a choice that you get to make. And in the best practices, I'll talk a little bit more about how to set it for different kinds of devices. What if you have multi-tier backend and all that sort of stuff? So as I mentioned earlier, that you get to set the shares, but what does this share setting exactly mean? What are we exactly dividing? And there are multiple units in the industry. For example, two of the common units that most of the people talk about is bandwidth, which is typically in megabytes per second, and throughput, which is IOPS. But if we try to allocate any of these two, they have potential problems. For example, if we try to do based on bandwidth allocation, where we say, oh, by the way, if you set ratio 1:2, we would allocate bandwidth in ratio 1:2. Then the VMs which are doing high IO sizes or the IOs with large sizes would unnecessarily get penalized because the cost of doing a 64K IO versus 32K IO is not double. So they would get penalized. Similarly, if we go purely in terms of IOPS, where we would say, oh, we would allocate IOPS to you, in that case, VMs that are going sequential access, they would again get penalized because the cost of doing sequential workload is much smaller on most devices as compared to the random IOs. And in the previous example, if you recall, I showed that two VMs, when I set ratios in 1:2, they got roughly IOPS in ratio 1:2. And there they would get IOPS in ratio 1:2 is because they were running almost the identical workload. So what exactly are we dividing when we say settings 1:2? So SIOC essentially carves out the total queue that you might keep pending on the array, and it says, I would give you the queue slots based on your share value. Now, if a VM gets, let's say there are two VMs, they get 4 queue slots each. But one of them is running random workload, other one is running sequential workload. In that case, the one running random workload would recycle the queue slots slower. The one running sequential workload would recycle queue slots faster. It depends on how array is responding to the IOs for that VM. So in that case, we would try to maintain the efficiency if the array was providing the backend efficiency for different kinds of workload that you might be running in the VM. And that's why we don't try to dictate either IOPS or megabytes per second onto the VM IOPS. Now, just to give a pictorial example of what it means to set the host level queue depth. Here we have 3 VMs, A, B, and C, with equal shares each. And their A and B are running on ESX Server 1 on the left-hand side, and B is running on ESX Server 2. Now, if you don't have the SIOC feature, essentially the VM B can get as much bandwidth or throughput as the other 2 VMs. And this is a simple example. If you have 10 VMs versus 2, you can see it can really get skewed. And there is no control on how to make sure that one VM cannot impact the performance of other VMs. With SIOC, what happens is that the host 2 on the right-hand side, which is only running one VM, his queue depth would get throttled. So essentially, the number of queue slots that are available to each VM is going to be roughly the same. So if the total queue depth on the array is 60, each VM might get 20 each. And how do we determine what's the total queue depth? That's based on a mathematical control equation that we have designed, which says that we would dynamically figure out what should be the total based on the current latency. And if the latency gets lower, we increase that queue depth. If the latency gets higher, we decrease that queue depth. But we make sure that the overall latency on the device does not go above 30 millisecond or whatever congestion threshold you may have set. So again, with SIOC, all VMs get equal queue slots. Now, if you had a skewed distribution where you have VM A with much higher shares and B and C with 500 each, you can see that again, based on the share values, it would figure out what should be the exact queue depth. And in reality, the way the whole piece works is that SIOC figures out what should be the queue depth at the host. So it would give a smaller value and a larger value. Now, a host can see this much. But then we have another scheduler that runs within the host that says, oh, by the way, this is the queue depth at the host. I'm running 20 VMs on this data store, and now I'm going to figure out how to give how much to each VM. So it becomes a 2-level approach, and using the combination of these 2 levels, we get the end-to-end control of VM performance isolation. So you can see in this case, the slots are proportional to the overall shares. One thing I should mention at this point that, as I said, none of this is static. If one of the VMs here stops using the slots, that means that the VMs running in the system would automatically start using those values. It's not something that one VM goes idle and those slots are wasted. It's a completely work-conserving scheme. Now, once we introduce a feature, we need to actually also introduce few metrics that would help you see if the feature is working and how well it's working. So in this case, these are some of the stats that we launched as part of vSphere 4.1 when we released it on VMFS. And the same stats are available on NFS now. The new stats are essentially, one is the storage IO control normalized latency, which I'm showing on the left-hand side on top. What this does is it gives you the overall latency seen on the data store across all hosts and all VMs. Now, you can have a lot of other stats that you can look at, for example, per host latency for a data store, per VM latency for a data store. But this stat gives you the overall view of the world. It essentially aggregates the latency across all hosts. It does a weighted computation based on the IOPS that each one is seeing, and based on that weighted computation, we draw that plot. And by the way, we also normalize this value based on the IO size. So in some cases, you might see a slight discrepancy where you are doing 128K IOs, and the latency that you are seeing in, let's say, ESX top or somewhere is 50 millisecond. But this chart might show you 40 millisecond. That's because we normalize the latency based on the IO size if the IO size is very big. Second is SIOC runs in a very dynamic manner. What I mean by that is it actually looks at the latency value every 4 seconds. And every 4 seconds, it reevaluates what should be the host level queue that I should allocate based on the VMs that I'm running, based on the shares that those VMs have, based on the demand that those VMs have, and all that is considered while deciding that queue depth value. And we also have bounds to make sure that we never fall off any edge. So the lowest queue depth, even if your host goes completely idle, your VMs on the host are not doing any IO whatsoever, the lowest value we set is 4. And as soon as the workload comes up, the value would again start to increase. And on the left-hand side bottom, that's exactly the plot we are showing is the queue depth value per host. So if you see that plot to be a flat line sitting at 64 or 128, some default queue depth value, you know that your data store is not seeing performance problems. Your latency is smaller than the congestion threshold that you have set. As soon as you see in that plot that the queue depths are varying, that means SIOC at that point is kicking in and actually watching your back, making sure that the performance degradation doesn't happen for critical workloads, and it will give you that peace of mind. And by looking at that plot, you can even see how often it is kicking in. If it kicks in very often, if it's kicking in 16 hours during the day, I would say you should go and buy some more storage or increase the performance of that storage, because at that point, you are literally running in congestion mode most of the time. But in cases where this happens during 1 hour a day, half an hour, 2 hours, that's when you don't really need to buy more storage now. You can say, during these bursty windows, the feature is really saving you, and you don't have to buy more storage just because of half an hour during the day. But at least you would have the peace of mind of still putting workloads on that NFS data store without worrying about the critical VM getting hurt in that half an hour that you care about. Now, let's talk about how it really works in practice. And we'll go through 3 different use cases to highlight different properties of the feature and explain the features that I talked about, that it's dynamic and it takes care of the VM importance and demand. All that we'll show using the case study. So let's first briefly touch base on what's the common workload that we are using. For most of these experiments, we are using a DVD store, which is a open source benchmark available, and it basically tries to emulate an e-commerce workload. Now let's start with the case study 1. This is a very simple example just to show how it saves a critical VM from a bandwidth hogger. So in this case, there are 2 hosts. Each one is running a VM. The host on the left is running an IO meter VM, which is just to hog the bandwidth in this example. And the host on right is running DVD store, which is your critical VM running some e-commerce website or something that you really want to protect. Normally, people would put them on two different data stores. And that's the silos that you end up creating, where now, in order to put 20 different workloads, you might have 6 different silos. And that's exactly the feature we'll try to avoid, that you don't have to create data stores just because your workloads have different needs. So in this case, we have a single NFS data store, which has all the data and index file of the DVD store, and it also has the virtual disk for the IOmeter workload, which is running all on the same NFS data store. And the IOmeter workload is essentially doing 64 KB request random read while keeping 12 outstanding IOs at all times. I mean, this is really saying that whatever is left on this array, I need to get it. And the DVD storage we are running with 72 users with 500 millisecond think time. Now let's see what happens when we just run DVD store. You are in your silo environment. You say, by the way, I will run it separately. It's a critical workload. And you get some standalone performance. We have normalized that performance to 1. So we are saying this is a standalone performance. If you were running in complete silo, you would get this performance. And the performance here is measured in terms of overall throughput of DVD store in terms of orders completed. Then we run the same scenario without SIOC, and we have these two VMs running the workload on the same data store. You can see the performance essentially drops by roughly 35%. Now that's the impact just because now there is contention on the data store that you are seeing. But we turn on SIOC after that, and the shares value is 500 and 2000. So we gave higher shares to the critical DVD store VM. And you can see the performance now comes back to roughly 82% of the peak performance. Now you'll say, gee, 82%, is that good enough? First of all, if you notice the shares that I have set here, the shares are 500 is to 2000, which means you are essentially telling that it's okay for this low priority workload to get 20% of the overall throughput, because he has 500 shares out of 2500 shares. And if you see, it is actually getting 18% of the throughput. I mean, you said 500 versus 2000, that's what we are going to honor. If you really wanted to push that bar even higher, you can set 500 and 4000, and you would see the bar would get pretty high. But when DVD store goes idle, let's say in the evening it goes idle, at that point the other VM would be able to get the full performance on the array. And that's where the share-based control comes in. So here in this case, with SIOC, you get IO prioritization, you get better performance during the periods of contention that you care about. Now let's look at the second case study where I talk about what happens when things go idle, because things are not always backlogged on your data stores. So in this case, we have 2 ESX hosts. They are running 4 VMs, 2 on each, and all of them are running DVD store. But one of them is more critical than the other ones. Some of them could be customer-facing, some could be doing some internal tasks. And all of the data and index file for all 4 VMs are on a single NFS data store. In this case, we have set the shares to be 1,000 for the non-critical VMs, all 3 of them, and 2,000 for the critical VM that we are running. Now, let's see what happens in the beginning. So initially, all 4 VMs are active. And you can see on the top side, I'm showing the overall orders per second for each of the individual DVD store VMs. And on the bottom, I'm showing if you have a total value of something, what's the percentage each one is getting. And you can see here is that the VM with higher performance, higher shares, is getting much better performance from the array. Now, what happens when the critical VM that you wanted to protect goes idle? So in phase 2, on the x-axis, it's the timeline. So we run that, and we stop the workload in the critical VM. And you can see almost instantly, in a matter of few seconds, the performance of other VMs ramp up, and now they are getting much better throughput because the high priority VM has gone down to 0. But note that overall, their shares are still preserved. So the remaining 3 VMs that are left at the bottom, you can see they are still getting roughly the equal performance because they have equal shares. If we had set different shares there, you would see that in that period when there is more capacity available, again, it would meet in the ratio of the shares. Now, what happens when it comes back? How long does it take for it to get back what it gave up? And it has to get it back fast enough, otherwise giving up would be too hard. And in this case, as soon as the VM comes back and the demand comes back, again, within an order of few seconds, it is able to get the performance that it asked for. And that's the overall dynamic nature of the product. And again, you can see at the bottom that the overall percentage that they get, this VM gets much better overall performance as compared to the low share VMs. Now, what happened in this experiment under the hood? How did it work? And that's where the QDepth setting comes in, which I mentioned earlier. So what's happening initially, you have 2 hosts, and if you compare the shares of the 2 hosts, they are roughly in ratio 2:3. And on the top, I am showing the actual QDepth from the host during the experiment. And you can see that the QDepth that the hosts are seeing are roughly 10 and 15. So they are in ratio 2:3. And then furthermore, the host would take care of the dividing between the VMs. Now, as soon as one VM becomes idle, the effective shares of the host 2, which was running 2 VMs, one with 1,000 shares, other with 2,000, essentially went to 1,000 because the 2,000 shares VM is essentially inactive. So as the effective shares go down, the QDepth pattern reversed, that one of the hosts is now, host 1 is getting much higher QDepth than host 2. Again, when the VM becomes active, you can see that the QDepth again becomes in ratio 2:3 when the VM is active. And this is the actual timeline we are showing, which means this tells you how fast the feature reacts. If in this timeline it took some time to come in, let's say 4, 8, or 10 seconds, that's the time that it would gradually come to the equilibrium where you expect it to be. Now let's look at a third study, which is SIOC in a data center. Now this is running in wild, where you have a data center, you have a bunch of workloads, and you have different patterns throughout the day. Again, in this case, we have 4 VMs, and it's a very similar setup. We have 2 DVD store VMs running on each host, and all their files, all the VMDKs, data and index are on the same NFS data store. Again, the VM4 here is the one which has highest priority. Now, in this scenario, what we did essentially is that we start with your high priority VM, and then we make other VMs come and go away. And here what we start with is this VM4, which is the high priority VM, which is active right now, which is getting a certain performance. And let's say for the sake of argument that you said, okay, I'll put the other 3 VMs on the same data store because I don't want to create too many silos and then have partitioning across multiple data stores and so forth. So initially it was running by itself, very happy. On the y-axis, I'm showing the DS, the DVD store throughput. So it's running by itself, getting pretty good throughput. Once you power on one more VM, VM3 becomes active. Now there is contention going on, and the throughput suffers by roughly 8%. And this is the scenario without SIOC. One more VM gets active, the throughput suffers roughly 19%. Another VM comes in, it gets to 29%. Now we could keep on doing this till somebody gets fired or you are in real trouble. But we stop at this point, and we stop the VMs. And again, we stop VM3, we stop VM2, and we stop VM1. And you can see as VMs go away, the performance comes back to normal. Now, this is exactly the situation that would avoid people from putting multiple VMDKs on the same data store. And in this case, we turn on SIOC with the shares value of 500, 500, 500, and 4,000. And now this is really stress testing the feature because, one, we are putting 4 workloads out of which one is high priority, And second, all workloads are active and really pounding on the array. If you have more dynamic scenarios, the numbers would look even better. I mean, here we are doing stress testing of the feature. So in this case, again, we start with VM1. It's VM4. It's active. Nobody else is running. It gets a pretty good performance. When the next VM comes in, it takes a certain amount of hit, which you would expect because now there are two workloads running. There is enough there is some contention at the box, and it would see some performance degradation. Then the next VM comes in, it goes to roughly 16%. Another VM comes in, it roughly remains the same from 16 to 17. And in this case, based on the shares that you have set and based on the actual demand, there would be almost a lower bound on how much you can lose. And in this case, 17% is where we looked at, and that's where it almost stabilized. And it was getting now a bigger chunk of the queue to keep its workload going pretty well. And as we stop the VMs, the workload performance comes back up again. But the high-level point here is that as you set the shares value, you would see that there is performance differentiation. And as long as you can take a certain amount of hit because of putting a lot of VMs together, it's actually worth doing it with the feature turned on. And the main benefit is that if you create actually silos, you lose the benefit of statistical multiplexing. If you create different RAID groups and you say this is 5 disk, this is 5 disk. Now when workloads are idle on this, these guys cannot make use of these disks. So it's better to actually have a bigger group shared across VMs using a soft feature like this, so that when few VMs got idle, other can actually get the full performance of the data store. Otherwise, you have strictly partitioned the performance, and you would never be able to share the benefit. So the overall impact in this case is much smaller during congestion. Now let's look at some of the best practices to actually run the feature. There are essentially 4 best practices that I'm going to talk about here. One is if you have different data stores running on the same set of physical drives. So you have created a RAID group, or you have created some NFS aggregate on which you have put multiple data stores. Then try to run the feature on both of them and run it with same congestion threshold. And here is why. If you run it on one data store and not on another, it's essentially TCP versus UDP. You are saying this data store, when there is latency is higher, the ESX host would behave nicely, they would throttle, they would do all the things. But on this data store, they're not going to do any such thing. So now one data store is running in this TCP mode, other one is running in UDP mode, and now you would unnecessarily affect this. And this is a scenario we actually guard in the feature. In the feature, we detect this situation that if we see that we are reducing the queue depth, but the latency is not going down, somebody else is running on the data store. And we actually send you an alarm saying, by the way, this is something that may be happening. You may want to take a look at it. And either you can turn the feature on for all those data stores, or you can turn it off for all those data stores. But we look for it and we guard you. And we have actually built another nice control there that if we see this happening, where one data store is reducing or behaving nicely and the latency is not going down, we actually make it more aggressive in not reducing it. That the feature basically detects it and it says, oh, by the way, somebody is not behaving nicely with me, and it gets into this special mode where it says, I'm not going to reduce too much either. And periodically, it would bump up the queue depth and see if the other guy has gone away, or should it stay in this aggression mode. And so we are guarding your back there, but this is just, you might get the alarm, and it will tell you that this is something that the feature is observing. And we have seen actually very interesting cases where people didn't know this was happening, but once they saw this alarm and the definition, they realized, oh, this is what was going on, and I didn't even know that my production and some other data store were sharing the same set of spindles. Exactly the similar issue is this best practice 2, where we recommend that you do not share the access of the same data store with some non-ESX workload. And it's essentially the same TCP versus UDP issue, because all the ESX host would play nicely, they would throttle, but this external guy will not. And as far as we are concerned, an older ESX host before 4.1 is an external guy, because an older ESX host before 4.1 is not running the nice TCP algorithm and the control equation and all the math we are doing on 4.1 host. So if you are turning the feature on a data store, make sure that all the hosts connected to the data store are 4.1 or newer. Third is about the congestion threshold. So we have discussed this thing quite a few times now. What should be the congestion threshold setting? Based on some of the experiments we have done for solid-state disks, if you have paid enough money to get solid-state disk-based LUNs, you can set it much lower. You can set it to 10 millisecond, 10 to 15 is what we prescribe, but you can set it to a low value, because at that point you really want to run that data store at a much lower latency, and the feature would kick in as soon as the latency tries to go higher because of a lot of queuing going on the device. For fiber channel disks, 20 to 30 millisecond is a good range. For most of the cases we looked at, even if you set it to 20 millisecond, you are essentially operating at roughly 80% of your peak throughput. And if you care more about latency than really trying to get every single IOP out of the data store at the cost of latency, then set it to the higher end of the range. But if you are latency sensitive, set it to the lower end of the range. Similarly for SAS and SATA, for SATA disks, they tend to have a much higher seek delay. And for them, 30 millisecond is sort of the lower bound. If you set it to 30, it's still a reasonable setting, but if you want, you can change it to higher. Now here comes the interesting pieces. The new arrays like EMC fast or auto-tiered LUNs. There, the issue is that we don't know what exactly the configuration of that auto-tiered LUN is. We don't know how much SSD is in there, how much disks are in there. And there we recommend that you can either go with the vendor recommended value, or you can use the recommended threshold for the slowest storage, so that you make sure that you are utilizing all the tiers in your auto-tiered LUN. But at the end of the day, for any of these, it's also an application-dependent setting. If you really are running a workload that is latency sensitive and that's what your goal is, you can set it to a lower value based on your application. Fourth, so in vSphere 5, we have launched a very cool feature called storage DRS. And both features are designed by the same engineering team, and they play really well with each other. And they are very complementary. What SIOC does, it says, you have put these VMDKs on this data store. It could be NFS or VMFS. I'll make sure that the critical ones on this data store do get better performance as compared to non-critical. But who is to avoid the situation where one data store is running 50 VMDKs, other one is running 5, and now he's operating at 20 millisecond, he's operating at 10 millisecond. And that's where storage DRS comes in. It would actually do the load balancing across data stores to make sure that you are running roughly the equal load on all data stores based on their performance. So if one data store is high performing than the other, he would get the more number of VMDKs and more load. And that's why the features, they play very nicely with each other. And because of this, when you turn on storage DRS and you say you care about IO load balancing, SIOC gets turned on automatically. Because what we don't want is a scenario where one data store is running SIOC with 30 millisecond congestion threshold, others are not running, and storage DRS migrates a VM from this guy to the other data store. And now earlier he was seeing nice behavior because the SIOC was protecting the VM. Now nobody is protecting it. So since the feature plays so well with each other, we turn SIOC on by default on the data stores in the storage DRS cluster. And this basically also ensures that when storage DRS migrates a VMDK from one data store to another, the shares would get respected on the destination also. That's the key value proposition. And storage DRS has a lot more to offer than what I just mentioned in 30 seconds. And there was a talk today morning, but there are other talks during the rest of the week. And I would highly encourage everybody to attend the talks. So to conclude, SIOC provides you the necessary performance isolation that you need in order to really put VM decays or multiple VM decays on a single data store and do consolidation. So let me ask that question again. If your VMs are seeing poor performance, what's the 4-letter word that comes to your mind as a sysadmin? So now you can use a different 4-letter word. Okay, so what's next? And here I'll discuss 1 or 2 things which we are sort of looking at, and I would like to get feedback from you guys that do you care about that control? And if you do, we have actually some members in the audience. Our technical director, Bala, is here. I would encourage you to talk to him as well. And Ann Holler, who is our senior engineer in the team, she's here. So for other detailed questions or anything, you can talk to these guys as well. What's next? So one thing that we have heard from people since last 1 or 2 VMworlds is I/O reservations. Now let me just quickly ask, how many people here care about getting I/O reservations? Okay, roughly 10, 15 people or something. So, but this essentially what shares does, it gives you sort of a weighted allocation so that if you put more VMs, the value of the share gets diluted in the sense that if you run 10 VMs each with 500 shares, the share is roughly 10% of the data store capacity. But if you put 20 VMs each with 500 shares, one VM is going to get roughly 5% instead of 10%. With reservations, it would essentially try to reserve the overall IOPS for the VM decay that you care about. And the reservation can be done on a per VM decay basis or at the per VM basis. And is this something that if you would like to see, would you like to control how much you want to reserve on the data store? Like to control? Okay. And would you like an absolute setting there, or would it be okay to have a percentage of the peak, where peak is something that we estimate based on our stats? Percentage? Okay, okay.
Weird environments where you're doing performance testing, and regardless of how many VMs you run, you want them to behave the same because 5%. That's an awful huge thing.
So, I mean, I think it's very hard to do that regardless of how many VMs you run, you get the same performance. I think that kind of magic data store is hard to get. But if the data store overall capacity is very high, then up to a certain point you can get that behavior because the overall capacity is much higher than what you are currently running at. But there is another tricky thing that we are sort of seeing with reservation, and let me give you a sneak peek into that. The actual VM allocation that you might get can actually vary based on the concurrency. And here it's a simple law of statistics. This is not something that we can go against. And let me explain that behavior. Let's say you are running your data store at 20 millisecond latency. So in this table, I'm showing latency, which is the latency that which you want to operate the data store. Which means that if you now run a single-threaded workload, since the data store is operating at 20 millisecond latency, you can essentially get 50 IOPS on that single thread. So if your VM is doing IOs using a single thread, you will get 50, like a DD workload. But as an admin, you come in and you say, by the way, I want 200 IOPS reservation for this VM. What that essentially means is that if you have roughly the concurrency of 4, or at any time over a period of time, you overall keep 4 outstanding IOs, or you have enough parallelism equal to 4, you can get to 200. But if you just have a single-threaded app, 200 is an infeasible reservation at that point. And the same is partially true for even multiple vCPUs. If you have 8 vCPUs and you set the reservation of the VM to be 8 gigahertz, and your one core is running at 1 gigahertz of capacity. If you run a single-threaded app in that VM, it cannot get 8 gigahertz. And that's exactly the same Little's law of statistics that we run against. That it's a setting which is hard to give independently of your workload, And this is something that one has to be aware of while looking at it, while troubleshooting it, and all that sort of stuff. So the question is it okay if the allocation is actually based on this concurrency that you might have in the application? Is this something that is acceptable to have? Okay, let me go into the next item, and then we can discuss about more gory details later on after the talk. Next is, so far all the controls are specified at the VM or VMDK level. There is no resource pooling. What that means is that you have to essentially set controls at the per VMDK level. If you have 100 VMDKs, you set in 100 VMDKs. But we have been doing resource pooling for CPU and memory for almost 6 years now. And in this case, would you like to have something where we allow a similar resource pooling benefit where you can create a small resource pool and you can say, I want to give these set of VMs or VMDKs this setting, and the setting would be applied on that group and not just VMs. So there are two nice benefits that come out of it, is that one, you can create this hierarchical tree and you can subdivide it to different people and then they can make their own changes. So it allows you to delegate more easily. Second, you don't have to set the VM level controls all the time now. You can literally leave the VM level controls unset. And if you set a reservation at a pool level of 500, the sum of VM reservation would be 500, but you won't have to set manually saying, I want to set 100, 100, 100 each or something. Because if you set VM to be 100 each, then even if a VM goes idle, it's not that the other VM's reservation would be higher, because that's a value that you have set and you want us to enforce. But if in case you wanted to go to per VM level, you can still go to per VM level with the obvious restrictions that in the pool, the parent has to be greater than equal to the sum of children. So with that, I would end this talk. There is a lot of related material on this. We have done a lot of performance studies. There are other technical papers you can read to get even more gory details and to get deep dive into the product design. And with that, I would say the 4-letter word. Now you can say it. It's that you can use if you have performance problems. Thank you.